Hello, everyone. Welcome back. Today, we want to talk about the intermediate value theorem. So our goals then, as it says, understand the basic concepts, implications of what it tells us, the theorem tells us, then also be able to use the intermediate value theorem to prove that a zero exists between two values of a continuous function. So first off, before we get into the theorem, let's actually talk about what it means to be continuous. Let's remind you of that. Let's come over here to the right and hang on a minute. Sorry, I'm going to have to, there we go. Let me get everything, well, for some reason this is freezing in place. All right, everyone, bear with me here. I'm having a little problems. For a second, let me redo this so get everything set. There we go. Okay. Now, let's kind of remind everyone what a continuous and non-continuous function means. So if something is continuous, the function is continuous, what that means we have no gaps, no holes in the function, and also no asymptotes. Okay, so basic continuous, another way to say it, it's often says it's basically you can draw the function without ever having to pick up your pencil or pen. Let's also quickly just take a look at some non-continuous functions, some examples. Some examples. So for example, first I'm say no gaps. What no gaps would mean, measure of a function that looks like this. So maybe it comes up here and there's simply just a gap. Okay, so maybe this is our f of x. Okay. So because there's a gap there, it's not continuous. So once again, the idea, if I was drawing this function, I have to pick up my pencil or pen to actually finish drawing it. All right. Another example are no holes. So let's say we had a function that maybe is continuous everywhere, except this one spot has a hole. Okay. And remember, the hole means that point's not included. So even if it's continuous everywhere else, there's a little hole right there. Now, every point, every number really, really close to that is included, but it's not that one place. Once again, it's not continuous. And once again, you have to pick up your pencil to draw it. Okay. They call this our g of x. And then finally, let's say we have a function that looks like this, where we have basically a vertical asymptote. It looks like maybe like this. Let's call this our function h of x. And here, it still essentially is a gap. I just want to mention the vertical asymptote acts like a gap. So once again, function never crosses this line. It never touches that line. So I have to actually pick up my pencil to do that. So function that's not continuous, like these, is a function where something's preventing you from drawing it continuously. So basically, there's a gap, hole, asymptote, or something like that. Maybe some combination of all of them. Now, let's talk about what the intermediate value theorem says. So the intermediate value theorem says is you have some function f of x is continuous between 2 points a and b. So let's draw a picture here. And here, I'll just do this in the first quadrant just for simplicity, but it could be anywhere. Let's say this is our function right here. Actually, let me back up. Let me actually change that. Let's actually do this. We're talking about the intermediate value theorem. Okay, so let's say maybe our function looks something like this. Now, once again, what's simplistic is called as f of x. Of course, you could name it anything. Let's say this point, I have point A right here and a point B here. Okay. Now, if you think about this point on the graph, these y values, okay, once again, this is a continuous function. Okay. Now, think about this point right here on the graph, where it says the coordinates A and f of A. F of A is our y values right here. And then this point here on the graph has coordinates B, and then the y value we're going to call f of B. And so f of B is right here, the y value. So what the intermediate value theorem says, if I have a function that's continuous between these 2 points, A and B, and once again, it is continuous being the key, then f of x goes between or takes on every point between f of A and f of B. Okay, basically it has to, because if it's continuous and it goes from here to there, essentially it has to go through each one of those points for it to be continuous. Now, if it's not continuous, that doesn't necessarily hold. Okay, but if it is continuous, then it has to be true. So between some points A and B, as long as the function is at least continuous between those 2 points, then your y value is going to basically go through every y value between the y value at A and the y value at B. Okay. So look back at the other graphs we had, as we can see that wouldn't work for some of these. Okay. Think about the same thing. If our A here, A was here, and our B was here, then obviously it's not going to go through every f of A and f of B. Okay. Same thing here. If our A was here, in fact, let me just put A and B's here just for comparison's sake. That's an A, that's a B. Here's an A, here's a B. And let's say here is A and here is B. Okay. The same thing here. You know, if the function is not continuous between A and B, so it doesn't actually go through every value. So f of A would be right here, f of B would be here. It doesn't go through every value. In fact, I guess I can just put in those values. So this is f of B. This is f of A. So you see if there's a gap, it doesn't necessarily do that. Same thing here. If this is f of A right here, and this is our f of B, once again, it goes through almost all of them, but it still doesn't go through that once. It's not continuous. It doesn't go through that once. It's not guaranteed to. Doesn't mean it won't. It's just not guaranteed to. I should make sure that's clear. So the intermediate value theorem says it's guaranteed to go through at least that point. Maybe not everywhere, but at least somewhere. And once again, if this is my A's, this is my f of A right here in this graph, and this is my f of B right here, okay? So once again, it gives that gap. There's no guarantee it's going to go through every point. Okay, so once again, what the intermediate value theorem guarantees is you have a function continuous between 2 points A and B. If it's continuous, that's the key also. Then it has to go through at least somewhere, every point, y value between f of A and f of B. All those y values have to be included somewhere if it is continuous. If not, it's not guaranteed. It might still, but it's not guaranteed to. Now, let's talk about how we can use this. So the second statement below says the theorem also implies that for a continuous function, f of A, if f of A and f of B have different signs, that there's at least one real zero between x of A, x equals A, and x equals B. Okay, so let's just kind of draw, in fact, maybe draw basically the same picture again. So this is our function, the different function, but that's okay. So let's say this is A, and this y value here is f of A, and this is B. This y value here is f of B. Okay, well, clearly f of A, since it's below the x-axis, f of A is less than 0. It's negative. There's a negative sign. F of B, since it's above the x-axis, that y value is positive. It's greater than 0. Okay, so what that says is, since this is continuous, so f of x equals 0 somewhere between a and b. So f of x equals 0 somewhere between a and b. Okay, so somewhere, if it changes signs, either going positive, negative, or the other way, negative, positive, that means it has a 0 somewhere between a and b. Okay, it has to equal 0. Okay, so f of x has a 0 between a and b. It has to have at least one. It could have more than one, but has at least one that goes through every value. So basically, have a sign change between, once again, a continuous function, have a sign change between f of a and f of b. If it's continuous between a and b, and there's a sign change, it means there's a 0 somewhere, at least one. Could be more than one. Okay, and that can be really useful. And this is something that was especially really useful in the days for computers and calculators. When you did find out where 0 was, then this could actually help you find that. Okay, so let's look at some examples. At least use a function and see some examples of this, how we can apply this. So let's look at this function. F of x is equal to x to the 4th plus x cubed minus x squared. Okay, now what I've already done is I've used the website Desmos, and I've already graphed this. So let's take a quick look at it. Okay, so here's what it looks like. So plug this in, and we can see we actually have, in terms of zeros, here's what the function looks like in terms of zeros. Remember, zeros where the graph crosses or touches the x-axis. We have 3. Okay, here at -2, 0, here at 0, 0, and here at 1, 0. So those are our zeros of the function. Now, if you notice, this is also a continuous function. It's a polynomial, so that guarantees it's continuous. So what we can see from this is this is going to show us then that we can actually use the intermediate value theorem to show that we actually do have zeros between those two, to confirm that. Okay, so of course I'm showing the graph earlier. Imagine you didn't know what it looked like. And so let's take a look. So let's pick from, how about -3, x equals -3, and x equals -1. Let's do that one first. Okay, so once again, this function is a polynomial. So it's continuous everywhere. Space. It's continuous everywhere. Okay, so first, let's call this number 1. Let's prove there is a 0 between x equals -3 and x equals -1. Okay, so we just saw on the graph there is. How to prove that then? So actually what we need to do then is actually need to plug this in and find it. So let's do both f of -3. This is going to be a bit of work here. So -3 to the 4th plus -3 cubed minus -3 squared. And here we mainly just care about the sign. Okay, though the exact value is useful, we just mainly care about the sign of it. So let's check our calculator. Okay, so this, of course, is positive 81. -3 cubed is -27. And of course, -3 squared is 9. And that's going to be -9. So 81 minus 27. . 27 . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . is 45. The main thing that, of course, is greater than 0. That's the main thing we're interested in. So that's greater than 0. Okay. Now, let's do the other one. F of -1, okay, is -1 to the fourth minus -1 cubed minus -1 squared. Of course, -1 to the fourth is 1. -1 cubed is a negative, so negative plus negative is a positive. And of course, we have a -1 squared is positive, then -1. And so that's going to be okay, hang on a minute. Something is, oh, I'm sorry, that's a plus. There we go. I'll say something is not quite right, but I have the wrong sign right there. That's a plus. And so this actually, since this is -1 cubed is negative, that's going to be negative. There we go. Okay. So you can see this is going to be -1, okay, which is less than 0. Okay. So the intermediate value theorem, just abbreviate that, says that there is a 0 between x equals -3 and x equals -1. Once again, it could be more than 1. We know there's at least 1. So let me bring the picture back. Okay, and we can see right here is at -2. Okay. Now you could also do the same thing. You also say there's one, different places on the graph. Let's look at one interesting case right here. What about between -1 and +1? Maybe -1. How about -1 and let's see. How about -1 and 0.5? So one, but interesting here is this point right here. Okay, so -1 and 0.5. So I also want to show you the limitations of it. Okay. So let me ask this as a question. What about between x equals -1 and x equals 0.5? Okay. So as we'll see, if there's a sign change, it guarantees there's a 0. But if there's no sign change, it doesn't necessarily imply there isn't one. Okay. So we've already done f of -1. So f of -1 we just did. And that was -1. Which is less than 0. Now, let's do f of 0.5. Okay, and so we just have 0.5 to the fourth. So here's when to make sure you use your calculators. Plus 0.5 cubed minus 0.5 squared. Okay, so 0.5 to the fourth. Okay, this is going to be 0.0625 plus then 0.5 cubed is 0.125 and minus 0.5 squared, which is 0.25. And if we combine these, okay, so this is going to be 0.1825 minus 0.25. And so the main thing is whether it's positive or negative. You can see it's going to be negative. And so this is going to be negative 0.0625. Okay. The main thing that was less than 0. Okay. So no sign change. So I'll just call it the IVT for intermediate value theorem doesn't tell us anything. Okay. So this is one of the cases where the intermediate value theorem doesn't actually tell us anything. Okay. Because if we bring the graph back up again, you see here, negative 0.1 and negative 0.5, then obviously there is a 0 here, but if you notice, it actually just touches it, doesn't actually cross the x-axis, but just touch it. Okay, so we do have a 0 there. But in this case, since the signs are both the same for both values, is continuous there, the intermediate value theorem doesn't tell us whether there's a 0 or not. So just because there's no sign change does not imply there's no 0. It just means if there is a sign change, you have a continuous function, it means there's definitely a 0 between them. But it doesn't necessarily imply not getting that result doesn't imply there isn't one. I'll just say so no sign change doesn't mean there is no 0. There still could be. In this case, there is, but it just doesn't tell us that. So we need a sign change to tell us for certain there is one. Because obviously, let's go back to this one more time. Obviously, if you went from -3 to +3, f of your y values both be positive, and so from there you wouldn't know there are zeros at all. But as we can clearly see, there are 3. Okay, so quickly let's review what we've learned. So if you have a function that's continuous, and once again, what continuous means is there are no gaps, no holes, no asymptotes, like we see here in these 3 examples. As long as the function doesn't have any of those problems, as long as it's continuous, as long as you can draw it without picking up your pencil, then between any 2 points, function is continuous between any 2 point x values a and b, then the function is going to go through every y value between f of a and f of b. And if f of a and different b have different signs, that implies there's a 0 somewhere between a and b, at least one. Could be more than one, but at least one. But as we also saw, if there's no sign change, that doesn't imply that there is no 0. Could be 1, but just the intermediate value theorem doesn't tell us in that case. All right, so those are the basics of the intermediate value theorem. And it's just how you can use it then to prove where a 0 exists. Thank you. Have a good day.